All right, so today we're going to do something a little different. We're going to play detective and crack a really cool linear algebra problem. I've got this exam question here about a vector space that looks, frankly, a little nuts. Our mission? To break it down and figure out what's really going on under the hood.
Okay, so here's the plan. We'll start with this weird space U, figure out its basis and dimension, then see how it connects to good old R3, find our way back with the inverse, and then wrap up what we've learned. Let's jump in.
All right, first up, the mysterious space U. This is where our investigation kicks off with this kind of strange-looking subspace of polynomials.
So here it is in all its glory. U is the set of all these polynomials. Now look closely. See how the coefficients, the numbers in front of the x's, are all tangled up? It's not just any polynomial. They have to follow this exact formula. And here's the kicker, the big clue. Even though it's a cubic polynomial with potentially 4 different coefficients, the whole thing is actually controlled by just 3 little letters, A, B, and C. That's super important, so keep that in mind.
Okay, next section. Let's crack the basis and dimension. We're going to find the fundamental building blocks of U.
So that leads us to the big question, right? What is this space really made of? What's its DNA? If we could figure that out, the whole thing will make a lot more sense.
Okay, let's start with the general formula for any polynomial in U. Right now, it's a bit of a mess with all those A's, B's, and C's mixed together. Our goal here is to, well, it's to untangle them. Let's see if we can separate them out and see what each parameter is really doing.
And there we go. See what we did? It's just a little bit of algebraic shuffling. We've pulled out all the A terms together, all the B terms, and all the C terms. And just like that, the hidden structure pops right out. You can see that every polynomial in U is just some amount of that first polynomial, plus some amount of the second, plus some amount of the third. So these 3 polynomials right here, these are our building blocks. We call them U1, U2, and U3. Anything and everything in our space U is just a simple recipe, a linear combination of these 3 guys. That means they span the space. But, and this is a big but, for them to be a true basis, they also have to be linearly independent.
So how do we check for that? Well, a super handy trick is to turn these polynomials into coordinate vectors. It just makes things easier to see. And once we do that, look at this. You see that little staircase pattern with the zeros? That's what we call row echelon form. And the second you see that, you know for a fact that these vectors are linearly independent. No way can you make one of them by combining the others. It's impossible. So what does that mean? We have 3 vectors, they span the space, and they're linearly independent. Bam! That's a basis. So the dimension of U is 3. And that's really cool, right? Because U is made of cubic polynomials, which live in a 4-dimensional space. But U itself is really just a 3-dimensional slice of that world. First part of the mystery? Solved.
All right, next up, we're building a bridge to R3. We're about to uncover a pretty cool connection to a world we're all a bit more familiar with.
Okay, so this is the linear transformation, T, that the problem gives us. Think of it like a machine. You feed it one of our polynomials from U, and it spits out a vector in R cubed. And notice how it works. The coordinates of the vector it spits out are made from the exact same A, B, and C parameters that define the polynomial in the first place. That's not a coincidence.
And this is where things get really interesting. On the one hand, we have U, the space of polynomials, functions. On the other, we have R3, a space of simple vectors, just points in space. They seem totally different, right? But they both have dimension 3. Whenever you see that in linear algebra, the 2 spaces have the same dimension. A little alarm should go off in your head. It's a huge clue that they might be, in some deep way, the exact same thing.
So this brings us to the million-dollar question. Is this connection a perfect one? Is it a one-to-one mapping? The fancy word for this is isomorphism. If T is an isomorphism, it means U and R3 are just 2 different ways of looking at the exact same structure. They're basically twins wearing different outfits.
So how do we prove it? Well, there's a standard test for this. We check something called the kernel of T. All that means is we ask, what stuff in U gets sent to the 0 vector in R3? We set the output of T to 0, 0, 0, and see what input could have caused that. If the only thing that gets mapped to 0 is the 0 polynomial itself, then our transformation is 1-to-1. It's a clean map.
And when you actually solve that little system of equations, what do you find? The only possible solution is that A, B, and C are all 0. And if A, B, and C are all 0, what polynomial do you have?
the zero polynomial, so the kernel is trivial. It just has the zero vector in it. That's exactly what we wanted to see.
And that's it. That's the smoking gun. Because the transformation is one-to-one and the dimensions match, we can officially say T is an isomorphism. Our crazy-looking polynomial space U is, for all intents and purposes, structurally identical to the simple everyday R cube. They're just different labels for the same thing.
Okay, last big step, the journey back, finding the inverse. So we've built this bridge, T, that takes us from U over to R3. But what if we want to go back? We need to build the return path.
So our goal is pretty clear. Find a formula for T inverse. Basically, you give me any vector from R3, and this formula should tell me exactly which polynomial in U it corresponds to. It's the undo button for T. Now, the way we do this is actually pretty smart. Instead of trying to solve this for some generic vector, we just do it for the building blocks of R3, the standard basis vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. For each one of these, we work backward and find the one polynomial in U that T turns into it. We just have to solve that little system 3 times.
And here's the magic of linearity. Since T is linear, T inverse has to be linear too. And what that lets us do is take the 3 polynomials we just found, the ones that map to the basis vectors, and just stitch them together to make a general formula. Any vector in R3 is just A times the first basis vector plus B times the second plus C times the third. So the polynomial it came from must be A times the first preimage plus B times the second. You get the idea. And that gives us this, the final formula for the journey back.
So, what did we learn from all this? Let's put all the clues together and see what the big picture is.
So here are the big takeaways. First, if you have some messy, complicated space, the first thing you should do is find its basis. That simplifies everything. Second, an object's dimension tells you its true size and is super important. Third, this idea of isomorphism is incredibly powerful. It shows you that things that look totally different can actually be the same underneath. And finally, finding an inverse isn't some black magic. It's a systematic process you can always follow by mapping the basis vectors.
And this whole thing leaves you with a really cool kind of mind-bending question, doesn't it? This idea that completely different-looking things can be fundamentally the same pops up everywhere in math. So it makes you wonder, what other structures out there are just the same thing, but wearing a clever disguise? Something to think about. Thanks for joining me on this one.